Hello, welcome to our ELE Capstone Design project. We're Team Hexagon, and our title is SmartProcess, Planning for Inspection. Our team, Jonathan O'Hare, a product manager for Hexagon here in Kwanzaa and Kingston, graduated in '94 for URI. Najib, a data scientist, he's our consultant technical director. And Brandon, a software engineer, graduate for 2017. For the designers, we have James McHenry, a computer engineer, myself, also computer, and Pat Miller, industrial and systems engineer. A little bit about Hexagon. They were formerly known as Hexagon Metrology. They're today's world leader in quality control solutions for manufacturing companies, and they offer long-lasting partnerships with their customer base. They have amazing customer technical representatives. We had an issue with our CMM, and they reached back to us that same day. Project motivation involves a traditional manufacturing workplace where they assign specific tools and parts to specific machines. This is due to convenience or limitations. When a customer buys a CMM or coordinate measuring machine, it is a high investment at the start due to its cost. However, this machine will outperform the current method, and the customer will see a return in investment in a matter of weeks. CMM offers greater flexibility with more precision. However, currently, customers will spend an hour in the beginning of the day to qualify the red tip on the stylus or tool. The scheduling manager sees a list of tasks or a list of jobs to be completed throughout the week, and will assign a job to a time and to an operator. However, the scheduling manager only sees the list of jobs and not the whole process. They do try to minimize downtime, which is caused by changeover time, like the time it takes looking for a part, or the setup or breakdown time, to name a few. The SmartProcess is using smart technology which tracks a large data set and analyzes the data as a whole. Looking at multiple parameters, we can minimize downtime and have higher production rates. This is a block diagram showing our approach. We'll be using two CMMs. The one labeled Tempo can pick up and move parts on its own. With that comes an online asset manager called SFX. Also a data extractor script called Routine Data Explorer. We combine all the data from different sources, find out which parameters are key, and use a machine learning algorithm. Best anticipated outcomes is to come up with a model or algorithm to give insight to the frequency of probe calibration and qualification, the advantages of using a stylus rack, the advantages of using a Tempo CMM. Team accomplishments. SFX, the online asset manager, extracts the data from our routines that we create using PCDMIS. PCDMIS is how we code the CMM and test out experiments to get more data. The Routine Data Explorer gives us both dynamic and static output files, and we are using Python as our coding language for data aggregation. This is a simplified block diagram of how we are tackling this problem. First step is routines. To the right is an example of a schedule. Notice multiple CMMs are able to run whichever routine. By looking at timestamps provided in the dynamic output file, we can calculate the job changeover, part changeover, operator changeover, and the probe stylus calibration. When obtaining data for the whole entire process and not just the CMM itself, the sources are outputted in different file types. This is a screenshot of the dynamic text output file. It has the date and time each routine ran throughout the day, and each action inside the routine was taken. This is necessary for our machine learning algorithm to train and test data. For data collection and key parameters, we are going to be using a question flowchart that starts with the initial work schedule, calculates the OEE, overall equipment effectiveness, checks to see if there is a potential gain. If not, keep the schedule. If yes, then optimize the parameters. Next, we'll be speaking James McHenry, my partner.
What we'll be talking about is I'll be going through what I did with these routines, data collection, and other key parameters. First, we'll start off with routines. The part I'm working with is as seen on the right here. It's a block that has some holes in it. What I do in this routine is I go through and I measure each individual hole, and what I do is I use the probe to scan this hole. Doing this, we get multiple hits and gather a lot of data that we can use to compare against other inputs. And with these routines that we developed in PCDMIS, I've also contributed on setting up a probe rack in PCDMIS and making other qualification routines. With these routines, we can gather more data about what's going on with the probe. What we do is we take in data from the CMM using a data exporter. And what that does is it's going to pull items from the controller and put them into two different file types. My partner Juan, as previously mentioned, takes in the dynamic file, and I take in the static file. A static file is in a JSON format, and what we do is we use Python to interpret that using the pandas data library and also the NumPy array data library. And using these items, we can parse the data into a CSV and combine it all together, so that way it's easier to read and visually more comprehensible. Now, what's up ahead is collecting more data by using another system called the Tempo system. As seen in this picture, the difference between the Tempo system and the current system we use is the robotic arm. What the robotic arm will have us do is be able to load parts automatically, and that way we won't have to manually set up the parts. This will definitely decrease the amount of downtime between jobs, and we'll be measuring and seeing how much of an improvement it is. Other things we'll be doing is we're going to be getting an accelerometer to add to the machine. Currently there are accelerometers on the machine, but the current locations we don't think give us enough data, so we'll add another one to see how the forces affect probe decalibration. Addition to this, we're also going to be adding more probes than we're currently using, just to see if there's any differences in deflection and temperature and other environmental variables. For the economic impact of the company for what our project is going to be achieving is implementing a high value feature in the next release of SFX. What we are planning to have is a program that will assist in lowering downtime for customers, and this will be shown through the SFX program. Some future technical accomplishments that we have coming up to achieve our AVO are identifying parameters that cause downtime. How we'll be doing this is by looking at the OEE gains and or time savings, which we'll have coming out from programs that we've created. Other things we'll be determining is how often to calibrate probes. We have started collecting data on this, and we'll be continuing that through the next semester. Also, along with collecting this data, we'll be able to optimize the scheduling of jobs with more data and determining exactly how changing probes and when changing probes will make either faster or slower job schedules. I would like to thank John O'Hare, our technical director. He's been a great help in this project and guiding us through on how we should tackle this, as he's the main guy that we talk to at Hexagon. Another great consultant, Najib, he's our data scientist, and he helps us with thinking about how we're going to implement a machine learning function next semester. Another great help is Brendan. He advises us on how to tackle certain problems. along with Charles Hilton, an applications engineer that we talked to over at Hexagon, who assisted us in learning PCDMIS, and Sunak, a professor at URI who has looked at this project before and has thought of some ideas that we can implement.